It's for you.
Good morning, everybody. My name is Leonid Shumilo from University of Maryland. Today, I'm going to present you the presentation Agriculture Under Climate Change. I want to start with few basic interesting facts about this topic. So, one of the largest winter crop types in the world and commodities, it's winter wheat. It's the third crop by production. Over 766 million tons can be harvested every year, and second largest crop by export, that accounting over 38% of global trade, accordingly to the FAO statistics. Increasing temperature of 1 to 2 Celsius degrees can significantly reduce the productivity of this crop, and studies showing that global warming already causing in some regions the reduction in wheat production for almost 5%. New generation crop growth models forecast 15% drop in wheat production until 2099, caused by the climate change and shifts in the temperature regimes. Cropland, at the same time, responding to the climate change with the migration or expansion patterns. And as any other living species, it tends to grow in more better climate conditions for its growth. But in terms of like how this migration is going on, it's not so common as other species because it's assisted migration, and it's usually based on the decision making of the farmers that taking actions dependently to the production changes over time. Interesting also, we know that one of the main causes, one of the main aspects that allows to mitigate this process of changes in the global wheat production and global winter cropland production are the development breeding of more heat-resistant crop types. And second one are policies and subsidies. Like for instance, in the European Union, common agriculture policy have a specific subsidies for farmers that are growing important for food production and food security in Europe, commodities that are impacted by the climate change, and to reduce the loss of income of farmers caused by the reduction of productivity of these crops in some regions. It covered by the states and it covered by the European Union subsidies programs. So research questions regarding these questions are how to link climate change and agricultural migration, and how to quantify agricultural migration. We're going to discuss this here. And we're going to start from the basics, how first build the maps that allow us to see the changes of winter cropland. So my study is focused on providing global winter cropland maps for entire globe, and I will show you example for European region. So this is pretty easy to maintain and easy to build predictive model based on the Gaussian mixture models that allows to distinguish between winter crop and other crops over cropland mask based on the phenological features extracted from the MODIS long-term time series data. The idea here is it's impossible to see anything related to the climate change using only few years of observations. First of all, it's impossible even to define cropland using only a few years of observation, because if we will just build cropland map for a specific year, let's say 2018. And it has classes of main agriculture crop types, grassland, forest, water bodies, other land cover types. How you gonna like distinguish between what is grassland and what is agriculture fields that right now under fallow? It's impossible without providing information from previous years. This is why, for instance, FAO have definition of cropland that we consider cropland as the land that used for agricultural production for crop growing at least once in 4 years. So you need at least 4 years to first define what is your cropland. Similarly, we defined what is winter cropland in this study, taking 4 years observation because in Europe, 4 years it's common length of the crop rotation cycle. So at least if the winter crop is growing in this area, more usually it's or winter wheat or winter barley or winter rapeseed, it will be planted at least once in 4 years. So we are taking crop masks that were provided by the GLAD team, and you can find them in the research Potapov et al. Global Winter Cropland Winter Maps for 21st Century. Based on these crop maps, we are building our Gaussian mixture model based on the MODIS NDVI information in 200 by 200 kilometer grid. We chose 200 by 200 kilometer grid is because this special extent allows to avoid areas with very significant changes in terms of agriculture. In 200 by 200 kilometer grid cell, we can consider most agriculture is homogeneous, and winter cropland can will have similar phenological patterns. So after this, Gaussian mixture model allows us to classify our cropland into the two classes based on the NDVI values as winter cropland and not winter cropland. Also, we have to consider that fallow fields can have significant vegetation, especially in the beginning of the season. So we need to normalize our NDVI data based on the global average NDVI for this area to reduce the effect of high vegetation in beginning of season caused by other vegetation types. Also, you consider that your crop mask is also not a perfect one, and the other crop type, other land cover types like grassland or forestry that due to the misclassification was added into your set for Gaussian mixture can add additional noise to your map and also reduce capability of the model, slightly reduce capability of the model to give correct prediction. So taking all of this into account, you can actually build decent winter cropland map for your area of interest. And here's one of the examples of winter cropland map built for the Europe. But I use this model together with crop calendars to build winter cropland maps for other regions. So after building map for each year, we are stacking it based on the rule it's winter cropland if it was winter cropland at least once per 4 years to get the winter cropland map of and analyze the changes in the pattern of expansion or decline or migration of winter cropland over 20 years of observation. Uh, Well, I think on Friday or tomorrow you will see that one of the main tasks after you produce a map, it's actually estimate the area and build the correct estimator for area estimation. In this study, I used so-called two-stage sampling technique. It's also based on the Olofsson best practices for area estimation and validation. However, it consists in two steps. First step is defining strata of higher level and lower level. So my higher level strata will be the winter cropland change map. So I define in such classes as winter cropland loss. It's when in period from 2000 to 2003, I had winter cropland in this area, and from 2016 to 2018, winter cropland was not planted. Winter cropland gain is reverse if we had no winter cropland in 2000 2003 and winter cropland was planted in 2016 2018. Winter cropland stable is if in both periods we have we have winter cropland. Other crops if in both periods winter cropland never was planted, and other classes if it's generally other land cover types that we are not interested in, but they can have significant area, and we have to count it in our area estimation. Then we define in lower level strata is um, based on the uh, based on the fraction of cropland or winter cropland in our area of interest. So we use fraction of cropland, and we have um, such four types of strata. Is very low if we like winter if the cropland is less than 20% of the area of interest of the cell. So we aggregated our areas into the 10 by 10 kilometer grid cell and then estimated the proportions. And also we now can reduce the area of interest by accounting only those cells that have at least 5% of winter or 5% of the cropland. Um, it will significantly reduce number of samples that you need for error estimation, and it will also reduce the error that you're estimating because the largest class, other land cover types, area will be significantly reduced. So uh, very low density cropland is from 5% to 20%. Low is from 20% to 47%. High is from 40, it's over 73%. Medium is from 47 to 73%. These numbers I selected not randomly. I tried to select such thresholds to approximately evenly divide areas for four stratums to have plus minus equal number of cells of different types. Obviously, it was not so trivial, and it's impossible to have a perfect balanced classification for these four classes because one of these classes always will be the smallest or the largest. So just try your best to make it as even as possible. After this, I selected 70 samples of the first stage, and inside of each of this first stage strata, I also selected 20 samples of second stage. So in first stage, my sample is the 10 by 10 kilometer grid cell. In second stage, my sample is 250 by 250 meter pixel of my map that we're gonna then sample. So here how looking, so 10 by 10 kilometer grid cell. This is selected sample of the first stage. And inside, I selected 20 samples of second stage. If I had situation like here where I didn't have even number of samples for each class, I tried to redistribute the number of samples based on the areas of um, different strata types inside of the sample. So in total, I generated 1,400 samples for entire European continent. And I used model Sentinel, Lancet, historical data time series to label them and assign for each year the class, is it winter crop or not. And then similarly to our maps, I aggregated them into the 4 years interval to get if it was winter cropland or not winter cropland in this 4 years interval. So you should be familiar when you're starting to study your region of interest, how the signal of crop of your interest is looking. For instance, in Ukraine, this what I'm showing is absolutely very common and the perfect example of actual winter wheat signal, because majority of cropland in Ukraine, winter cropland in Ukraine, is winter wheat, and it has a very small peak in the fall, and it start emerging very early in the spring, and getting to very high values until sudden drop closer to the June, and in July it should be all harvested. Uh, Also, a good indicator of winter wheat is if you will have more dense time series of signals from different satellite-based sources, is that winter cropland can start emerging during the winter if the weather conditions are appropriate, and it can be hidden again by the snow after. So if you have very early vegetation on the cropland in that correlates with your crop calendar, you can assign the class of winter cropland to this cell. For some regions, you even can assign the more specific class if it is winter wheat or winter barley or winter rapeseed, depending on the region in which you're working. Because the studies for entire Europe, I was assigning class only winter crop or not winter crop. After sampling everything, now you can do area estimation and sample-based standard error estimation for your area estimation. And you can get approximate values of the areas for different years based on your like stratification grid. It will be also assumptions that error is similar in different regions. So it's more, this visualization of areas is more just like theoretical and allows to distinguish areas with highest changes and lowest changes. But what is very important to consider in your study is also the cropland change. So Europe is a region where we observe very little of cropland change in 20 years. In European Union, it's almost zero. The highest changes are actually happening in the Eastern Europe after Soviet Union collapse. A lot of agricultural land was abandoned, and like in 90s economic situation was not good to restore this land, but after 2000s actually a lot of investors and especially western investors started to invest in the agricultural land in the Eastern Europe, and we see that in Eastern Europe a lot of land actually was recalculated after collapse of Soviet Union in early 2000s. At the same time, in some regions like Russia, for instance, we see that some regions even with high economical growth, uh, investment climate, still have very high level abandonment. Usually it's more remote regions, and it's caused by the, like, for instance, the local population is not staying in the remote villages and moving to the more urbanized and developed urban centers, and it causes a significant portion of the cropland be abandoned. But in terms of climate change, the most interesting regions will be the south and the north. The south is where agricultural models are forecasting significant drop in production in the next 100 years. Meanwhile, northern regions of winter cropland and northern regions are reverse. The regions where we should see in near future the significant increase in winter cropland. But also, we have to keep in mind the limitations that cropland has, because a lot of areas that were calculated were that were cultivated um, already reached their historical peak. And if we have a new format cropland, usually it's, especially in Europe, it's related actually to recultivation of old farmlands rather than like land cover changes like deforestation that needed for cropland growth, like what we can see in Africa or like in South America, where like a large portions of the forest areas were um, cutted to clean the area for pastures or for cropland growth. In Europe, situation is more like most cropland that could be planted already planted, and there's significant geographical barriers uh, uh, like soil types or mountains, slopy areas that not allows to cultivate much more land. So this is more like steady region in terms of the cropland change. So interesting, what we can see for winter cropland is how it's intensified and expands in these regions of interest. So the southern areas of the Europe have more intensity of winter cropland, while northern areas have expansion. And you will see it in further presentation of Abyss in more details. He studied Russia intensification and expansion. In my case, I want to concentrate on some general areas and how it's related to climate change. So, in total, we see that in Europe, winter cropland, in the definition that the winter cropland lists once in 4 years, um, changed in 42 times, almost doubled the area. Significant changes happened, first of all, in Ukraine, Russia, Belarus, but on entire Europe also a significant portion of this cropland was created. Winter cropland was created due to the effect of the cover crops. So as you know, it's very common practice in the especially Western Europe, where farmers are planting winter crop in um, after harvesting their yield in the year of interest, and this cover crops emerges as winter crop early in the spring. It's actually winter crop for the next year. And here comes the problem of such study for Western Europe is that um, a lot of areas of cover crop actually, when farmers see that it has decent productivity and decent quality, can be harvested, and other areas will be um, terminated to plant spring or summer crop. So it's like making it very hard to study winter crop for Central Western Europe. But in terms of area estimation, still we see significant increase of winter cropland from 2000 to 2019. But what is more interesting, so this is how this contribution in this area changes contribution of different latitudes for this area changes. So as you can see, the highest changes actually happened in the central latitudes, and this latitudes also corresponds to the post-Soviet countries like Ukraine, Russia, and Romania. But we also see that significant increase happened on the north. And if we will look not just on the absolute values of winter cropland change, but the relative values of winter cropland change over total cropland area, actually the southern and central intensification and expansion are less significant than northern. The highest percentage of cropland that was cultivated as winter cropland actually was in the north. And it shows the expansion of the winter cropland to the north. And it's possible specifically because of climate change, because the climate conditions there was not allowing for winter cropland in early 2000s to have decent yield, because it was very short very short spring season, and the winter could be very cold, and it can cause winter kill for winter crops. And in a lot of areas, there was not enough of growing degree days to mature winter croplands enough for decent harvest. But recent years show that the situation already changed, and the countries like Finland can just like 1 year, like in 2000, I think 2018 or 2020, they just doubled the area of winter wheat for their harvest. And it's possible because now climate conditions are different, and we see like almost 60% growth in terms of yield and production of winter wheat for the Nordic countries. So this also can be seen on climate models. So in general, we have significant increase of growing degree days for entire world, for entire Europe. But like specifically in the north, the growing degree days like achieved the optimal value that good for winter wheat. And as you can see, trend of accumulated temperature, biological active temperature have two peaks, it's Central Europe and North. And if we are talking about correlation of winter cropland change with trend of temperature, from one side, it's moderate, it's 54% correlation. And it's not so significant if you will look on the like just statistics where the changes happened. It's caused because like for entire Europe, a lot of changes of winter cropland actually caused by policies rather than by the climate change. But in terms of temperature and average temperature changes from for 2000, 2003, and 2016, 2018, we can build predictive model for winter cropland change based on the growing degree days and temporal changes, and receive the model with R square 0.59 that is pretty significant, and it shows that actually this variable can give us predictive power to predict where the changes are happening. So winter cropland fraction and latitude have dependencies that can be research it through the growing degree days changes in the areas of interest. Another aspect of like studying the global agriculture changes and relationship with climate change is the technique that's called climate velocity. So the idea of climate velocity is that um, our climate is changing not only uh, temporarily. So definition of climate change is the change of temperature regime or precipitation or any other like climatic regime over time. Usually climate change described as temperature per year, our changes of temperature per year. But also climate changes spatially. So you know that like in some areas, moving like 10 kilometers to the north can reduce the temperature in 1 degree Celsius. In other regions, moving 10 kilometers to north can change temperature in uh, uh, 5 Celsius degrees. So it has different special gradients of temperature. So climate velocity is the variable that combines these two ideas in one as a climate change indicator that allow us to estimate how climate changes um, over time and space. So original idea it was just to estimate proportion of climate change and climate gradient and get the variable of speed and assign this variable to the climate change. So it's actually with which speed, especially agriculture velocity changes. But other studies show there's more efficient ways to estimate climate velocity with higher environmental realism. So this methodology calls climate analog velocity. The idea of climate analog velocity is that on your climate map, you have like temperature grid for 1 year, temperature grid for second year. And for each grid of interest, you're trying to find the climate analog grid cell in the next period of time. So, and then you are able to build so-called vector or trajectory of climate change um, by um, like studying the movement of grid cell over space and time. Uh, it allows to, first of all, predict how your climate changes spatially, and it also allows you to like to get a maps of uh, climate conditions for this period of time and where the same climate conditions will be in next period of time. So this approach used in biogeography to study the migration patterns of species because most species attempts to migrate in the direction of climate change. And using this technique, it's possible to predict the location in which the niches of species will try to migrate, and also it allows to um, estimate vulnerability of the species to the climate change, because if the optimal climate for surviving of the species will be further that they can migrate physically because each species has migration speed. Without assisting migration, where people trying to relocate the individuals of this species to new locations for their survival, they will extinct. They will not be able to survive because the climate change is uh, migrating faster. Their optimal climate conditions migrating especially faster that they can physically migrate. So this is very interesting concept, and it allows to build based on the climate condition maps. It can be like originally it's temperature, but like this approach considers that climate condition can be multivariable, and it's very good if you have more complex biological models of species. Like for instance, in agriculture, we know that temperature is only one of the factors of like growth of crop types, but we also have to consider precipitation regime. We have to consider growing degrees and etc. etc. This method allows to build multivariable climate change maps and climate change speed maps. So, for example, of the temperature, we can build the climate velocity map and determine areas with the highest and lowest climate change velocities, and use this information for further analysis of our land cover and crop type species and our expansion patterns. So from the global pattern, in terms of global patterns of the climate change velocity, we know that agriculture areas have 15% higher climate velocities than any other vegetational and cover classes. Such classes, crop types like cereals, sugar beet, and sunflower have the highest climate velocities in the global average. Uh, by the 15, 12, and 9%, it means that the areas where this crop types grows are more vulnerable to the climate change and will have more significant changes in the areas of these crop types. And 7.4 climate velocity vectors under agriculture, directed to other classes, the majority to grassland, tree cover, and shrubland. It means to for countries where these crop types are growing, uh, the only way to actually keep production on the same level for these classes will be the land cover change that will significantly impact the natural vegetation. So the countries where the climate condition changes more rapidly and will make such crop types like cereals, sugar beets, and sunflower less productive, they will have or to switch to other culture practices and plant more adapted to their climate condition crop types, or expand their agriculture through the uh, natural vegetation land cover types to keep the production on the same level. You can see this work in our article, Optical Flow of Temperature Reveals Climate Change Patterns for Agriculture and Forestry. Now let's go to the more country-specific examples. So we were working a lot on Ukraine because half of our team is Ukrainians. And Ukraine is one of the largest winter wheat producers in the world, and it in top 10. And at the same time, it has the highest density of winter cropland in Europe. So this is winter seal area over cropland maps, and you can see that Ukraine have a significant intensification of winter cropland area and winter cropland um, fraction for entire territory of Ukraine. We adopted the methodology for climate velocity to see how the winter cropland migrates or expands over area of interest using the fraction maps and standard error estimator from the sample-based approaches. It's absolutely the same technique as for climate change, but instead of getting the analog cell for climate parameters, we are using it now for fractional winter cropland parameter. And we can see that it's another work that actually introduced the idea of agricultural migration. So originally it was based on the FAO data on areas, and we have three types of like crop type changes in terms of area. So no adaptive migration, it's when the gradient of the migration of crop type um, is pointed in another direction than climate change. Adaptive migration, it's when the crop type change gradient is at the same direction as climate change. And the niche expansion, it's when the expansion can go in different direction at the same time, and we can see it's not related to the climate change at all. So this is the work that showed that from 1980s, we already can see the changes of major crop types in Europe that tends to migrate in the direction of climate change. Similar approach was used for Ukraine. So we have vectors of climate velocity that were estimated based on the temperature data and the um, and the climate analog approach. We also have vectors of agricultural velocity that were estimated in similar approach of agriculture fraction analog approach. And now we can build the map of agricultural velocity codirectionality with climate change. And we can see that the highest codirectionality can be seen on the northern latitudes. Um, so, and um, sorry, on the southern latitudes, and the intensification on the northern latitudes. So in total, winter cropland areas in Ukraine increased from 14.2 thousand hectares, millions hectares to 18.6 million hectares from 2001 to 2020. And over 9.3 million hectares of winter wheat is under climate change driven expansion. Conclusions that we get from the studies show that significant increase of winter cropland areas and fraction in Europe can have patterns that even though in terms of absolute areas, the most changes happen in the central latitudes, the fraction happen more in the northern latitudes. So the area increase has patterns of expansion to the north. Fraction of the winter cropland or total cropland area shows that northern latitudes have higher rates of expansion than southern latitudes, while southern latitudes have more intensification. Dependencies between winter cropland fraction change the trend of the accumulated biological active temperature for winter spring, indicating that climate change is one of the drivers of the expansion. And in terms of climate analog approach, this approach is applicable to the agricultural velocity to determine the not only trends but directionality of the expansion and changes in agriculture areas. Satellite data shows that 50% of winter wheat area in Ukraine expands in the direction of climate change from 2001 to 2020. It's interesting thing because this approach of agricultural velocity can be applied not only on the and this effect of migration expansion can be seen not only at the large scale like continent, but also on the country specific scales. Expansion effect depends on the climate conditions. In the latitude, the lower latitudes show the highest expansion, while the higher latitudes exhibit the highest intensification and the lowest expansion. The agricultural velocity technique can be utilized to study the impact of climate change on agriculture and the sustainability of food production. There are some reference that you can see that were used in the study. So the Slot, Lindsay L., 2020 climate adaptation by crop migration is the study that introduced the concept of migration of agriculture in response to the climate change and shows that in Europe the migration as adaptation is observable since 1980s. Igor Mayer, Climate Impact on Global Agriculture, emerged earlier in new generation of climate and crop models. It's very interesting work that also shows that areas where until end of this century we can observe the highest changes in majority crop types caused by the climate change. Skakun Sergey 2017 Ulysses large area winter crop mapping using modest and deviate data growing degradation information Gaussian mixture model is the article where you can look on the technique for winter cropland winter wheat mapping. Velocity of climate change algorithm for guiding conservation and management is the study where you can see the concept of climate velocity and how it can be applicable. Olofsson, good practice of estimating area and assessing accuracy of land change. It's the best guidance for your area estimation validation experiment. And Potapov 2022. Global maps of cropland extent and change show accelerated cropland expansion in the 21st century. It's a very nice and handy global crop map product that you can use in your study. Thank you very much for your attention.
Thank you so much, Leo. It's always impressive to see the amount of work and the amount of interesting insight that I can get. Always I see this presentation and how it evolves. We open the floor for the questions. I think you already have one, but please, you can share your questions in the chat or in the Q&A section. Thank you. Leo, I'm not sure if you can see the Q&A section.
I can't see, to be honest.
Okay, so I will just copy paste the question in the chat just for you to have it. Here you go. Okay. So if you see the chat, you have the
Okay, let's return to this. So on what basis strata threshold high 70s? Okay, so 10 by 10 kilometer grid cell was chosen because this is the resolution of climate data that were used for a study. The thresholds, so I originally chose 10 by 10 kilometer grid cell because it will be easier if we will estimate area in 10 by 10 kilometer grid cell to combine it with climate data further. The thresholds 73, 47, low 20, and very low less than 20 were chosen. So the algorithm of choosing was very simple. You are putting thresholds and changing threshold until you will evenize the areas and number of a number of population for each strata type. So I tried to put these thresholds in the way that number of cells with this like thresholds will be the closest to the even number. So they will have the most similar number of cells. So it's very common practice. You're trying to make population of each your strata type have like the same number of cells.
The second question has to do with the accessibility to the data that you have used.
So the data that I used, crop masks, I used Potapov et al. Product that are free available, and in the reference that I provided in the end, Potapov et al. 2022 study, you can download this data globally, and you can even use it in Google Earth Engine. And the MODIS and DVI data are free, and they are distributed by NASA. My winter cropland maps gonna be publicly available after I will publish my work. So it's right now not published results, and I'm not able to share them. But when it will be published, all this data will be publicly available. In terms of climate data, I used um, NASA climate models and satellites that also free available through the NASA portals or Google Earth Engine. Uh, Climate velocity map is on Zenoda. It's publicly available, and if you will go through this link in the data section of the article, you will have links to download climate velocity maps. How uncertain are the climate velocity estimates predictions? I don't understand this question. Like the climate velocity estimation have the same uncertainty as the climate data originally. So more accurate climate data you're using, more less uncertainty you will have in climate velocity. Nice presentation. I have a question regarding climate velocity. What datasets are used for calculating this? Thank you. So climate velocity was used based on the NASA global NASA GLMS model that provides data in 10-kilometer resolution and 50-kilometer resolution, and for some region even 1-kilometer resolution. Thank you, Leo. This amazing presentation. Can we consider integrating hydrological models to account the climate velocity, for example, by using a Q-stable approach to represent the balance between water gain and loss due to irrigation as a key for yes. So as I said before, what is great about the climate analog approach. So you can consider the input data as multivariable raster or multivariable vectors. So you have just to redefine your similarity metrics. Like in terms of one variable, it can be just the metric of difference, and originally you estimated the difference between two cells, and you have so-called dissimilarity threshold that allows to include uncertainty of your climate data, and say, like, for instance, if the climate difference between your cell 1 and cell 2 is less than 0.05 Celsius degrees, we consider it as insignificant difference, so they can be considered as equal values. If you're using the more multivariable approach, you have to redefine the similarity threshold. It's usually very simple by just analyzing the analyzing distribution of data inside of your area of interest. It can be used 95th or 85th percentile for this purpose, and you can stack as much data sets as you want of similar spatial and temporal resolution, and use, for instance, Euclidean distance or other metrics to define the similarity function between your datasets. But the idea is, like, it's very simple actually to use multivariable datasets with climate analog velocity, and you can include any important dataset for yourself, and you can change, like, for instance, some crop types are in some regions are not so dependent on the temperature, but more dependent on underground water, soil moisture, precipitation, and some other climate variables. So you can stack all of them and use as input to your climate velocity. So as you can see, even like in this figure, I did not specify what input is because it can be anything. It depended on your study. It depends on what is significant variables for your study of species of crops or like other biology. Uh, have you considered applying machine learning? So with crop mapping, I have very high experience in terms of applying machine learning for producing crop type maps. But the problem is when you're working on large extent, it's very hard to get the training data sets for machine learning, and more accurate and more technological machine learning methods you're using, more training data they require, and also then you have to validate. For me, also in terms of classification, to be honest, you don't really need very accurate map. You need the map that will allows you just minimize number of samples, because their estimation was conducted based on the samples, and actually you can just throw samples over any available map and you will have decent accuracy. You will see it further. In terms of studying climate velocity and agriculture velocity, uh, the stuff that I showed are more basic, but in my study that you can read here, I'm using more advanced computer vision approach for studying spatial and temporal changes called optical flow. Thank you. And models that can be useful for these factors. Can you please specify, thank you, this webinar, is there any AI models that can be useful for these factors? Can you specify which actually factors you're interested in? Because for climate velocity and the agricultural velocity, I'm using optical flow, that is more advanced computer vision techniques. For classification, any machine learning can provide a good result. Also, in terms of area estimation, this example gives more generic example of estimating area, but you can use also the regression-based estimators to get your areas over special distribution of areas. What is pixels? Large area is 1 pixel, and how did you verify the pixel? Like only checking the NDVI time series, or also visited fields like in situ data? So in terms of in situ data, our team had some in situ samples in Ukraine that we used for validation. We also use there's available free data set from that published by Ministry of Agriculture of France, that have polygons of agriculture of different crop types over France. But getting actual ground truth is very hard. This is why we limited our experiment with these two data sets. But in terms of sampling, uh, because this example is not crop specific, it's more is it winter cropland or not? It's crop seasonality specific. So the sampling technique that we used is more than accurate. That is very accurate for our area of study. So we actually like don't really need a lot of ground truth data for validation. The main complication is actually, yes, spatial resolution 250 by 250 meters. So in our experiment, sampling experiment, we tried to label those areas where we can see the signal of winter cropland on both like higher resolution data like Lancet and Sentinel, and at the same time the signal is clear in modest sample as winter crops. And if we don't have a clear signal of winter crop, and but at the same time have some signal on Lancet and Sentinel, we consider it as a mixed pixel and label it as not winter crop, because if the signal on Modis pixel is not clear enough, it means that winter cropland probably is not a majority crop type within the sample. Within the pixel. So this is important thing to consider, that when you label in such stuff on low resolution data, you're trying your best to sample your to label your uh, pixel as winter cropland only if you can see on the signals that it's not mixed pixels, that majority of the crop types within is actual winter cropland. I'd like to know if you have compared your results with field results in order to validate your results or to make calibration and adjustment. So the statistics and trends that I'm receiving for some countries like Ukraine is like corresponding to actual statistics, and also we use the Eurostat data to also like get additional validation in terms of trends that we are receiving, and it corresponds with the Eurostat data set. Appreciate the depth. Thank you. Yes, as I said, you can use precipitation data, you can use any data. For our study specifically, because Europe don't really have a large problem with droughts, and at the same time, Europe has very developed irrigation systems. Precipitation is not such significant factor in consideration that causes the climate change driven changes of crop types. Um, the more changes happens due to the growing degree days, and the main focus of our study is actually the northern regions where growing degree days changes, allowing now to plant to winter cropland, while like 20 years ago it was not possible. So, but for other regions, like for instance, Northern Africa, as valid expert here helping me, the precipitation will be much more important the growing degree days, because actually in Northern Africa, probably there's no season where you are not able to have harvest of winter cropland based on the active temperature variable, but the access to the water, access to the irrigation and precipitation is a more important factor. So it's really like when you're building your experiment on dependencies between climate change and agriculture changes, you have to consider these factors that some indicators, some climate variables are more essential in one regions and will have less impact on other regions. Meanwhile, the such factor as precipitation can switch significantly, because once again, let's compare Nordic countries, Baltic countries, and Northern Africa. The main impact there for expansion of winter cropland is increase in growing degree days that makes spring longer. Higher accumulative temperature allows to winter cropland actually mature and be harvested. Meanwhile, there's no problem with precipitation because there is a dense snow cover on winter that supplies like the most essential water in the early season. So when the snow melts, it's provides very large water budget that makes precipitation not so significant, and even can cause in some cases more harm to the plant, because soil moisture already have very high value, and a lot of crops don't really like excessive moisture, and it can cause to this more disease damage like wet leaves disease and etc. So precipitation is not so important on the Nordic countries or Baltic countries for winter cropland. Meanwhile, in Northern Africa, growing degree days already much more optimal than northern countries, but lack of precipitation, lack of the soil moisture, limiting the production of winter cropland. How do you handle the interval satellite images? Did you make a daily analysis? So here's the thing. So you need to do a seasonal analysis for winter cropland and for winter crops. Like if you are studying winter wheat, for instance, you need a lot of seasonal data to actually map where is winter cropland or winter wheat is. And the we are using Modis specifically because the Modis have everyday information, um, everyday like repeating sensing every day, and it allows to better extract phenology of our crop types. And it's very hard to do such studies using Lancet or Sentinel-2 because it will be very hard to train your models based on such datasets because like, they have lower spatial resolution and in some areas a lot of clouds that causing like sometimes you can have like only one image per month, and it's obviously impossible to map accurately winter cropland when you have one image in the like March, one image in the April, and that's all what you have. This is why like Modis is one of is so like strong data set that everybody can use because it have a daily sensing um, dates and very long time series, 20 years. So you actually can build interesting models based on this data set. Okay, if
Okay.
that's all, I think we can finish.
Yeah. Thank you so much, Leo, for the discussions and for the presentation. It was great. Well, we will get back at 10:30 to continue about dealing about climate. The second presentation will be about with Dr. Enenkel. He worked in the World Bank, and they developed a solution for addressing extreme climatic events through early warning systems and some financial also approach. So I will let Marcus tell you more at 10:30. See you.
Thank you. See you.